Okay, so today, did I share my screen? No. So where is it? No, yeah. So today we are going to finish chapter number 13, and we will start chapter 14. Let me just wait for the screen to come. And we basically stopped right in this problem. Okay, and let me put this like this. Okay, we're good. So so let me tell you, let me clean it up a little bit before we get started. Let me tell you what gonna solve this in very, very detailed way. Rather, I will try to, hopefully you will be able to go and solve it yourself at home. So let me tell you, what did we do? With this problem, we have a 2-teeth worm gear transmitting 1 horsepower at 1,200 revolution per minute, being engaged with a 30-teeth worm gear. The gear has a transverse diametral pitch of 6 inches, 6 teeth per inch, and a face width of 1 inch. And then we have the worm gear having a pitch diameter of 2 and face width of 2.5, and so on. So the quality of the material, we can use curve P to find the coefficient of friction. We discussed how the rotation is happening. So basically, I want to go right away to wait for it. It's coming. Yeah, here, right there. You know that maybe if I were you and I want to solve this problem, I would right away put the first equation in the solution is this one. There it is. Now, what happened over here, this equation will guide you in a sequential way to where should you go. You know, if you find the transmitted load, you can find other forces. And when you find the forces on the worm, you can go and find the other on the gear. And when you find the one on the gears, you're basically finding those forces that will load the bearing, which is the bearings that are carrying the shaft of, which is the carrying the gear. So this is a good start. So if I want to start with the W for worm along the transverse direction, which is, or the transmitted load, then it is 33,000 multiplied by the horsepower, which is 1, divided by the velocity, the pitch line velocity of the worm. Now, I don't know the pitch line velocity of the worm. So let me go back. The pitch line velocity of the worm is by divided by 12. Both of them are constant. And then the RPM, which is 1,200, which has been given. And then we have the diameter of the worm. The diameter of the worm is also given to us. It says a pitch diameter of 2 inches. So that wasn't difficult. This is VW, right? Now, so if I go there, I will put VW over here, and then I will determine WWT, which is 52.5 pound force. Now, I want to move on. Now, in order to move on, I need other parameters. So for example, if you want to find W, which is the resultant force, which can be projected into Y and Z, which means you will find the other component, then you need WX. WX is the same as WWT. That's what we talked about before. You can go while I'm talking and check the slides. Just a few slides in the back.
Doctor, where did we obtain the VG formula from? The pitch line
VG?
velocity?
What is that?
Pitch line velocity of the gear.
This one?
The first, yeah.
We didn't talk. Well, this one is the same as this one. This is not the first time, Hassan, that we solved we calculated the pitch line velocity. We have been always solving it. We did it with the spur gear.
Oh yes,
we
yes.
did it with the
Okay,
helical
general
gear.
formula, right? Okay.
Yeah, the same formula. So what are we gonna do? You look down, you see that you need phi n. Phi n is 14.5. It was given, but we don't know lambda, and we don't know f. So this is now we are being dragged one by one. Let me show you how are we going to calculate lambda. For calculating lambda, you need to calculate the inverse tangent of the lead divided by dw. We know dw, it is 2. We know by it's a constant. We don't know what is the lead. We want to find the lead. The lead is px multiplied by nw. Nw is the number of teeth for the worm, which is only 2. But we don't know px. We go back up to find px. For worm and worm gear, it's the same as pt, which is equal to pi divided by 6, the diametral pitch. So when we do that, we got px. We substitute px in here. We find L. We put L here. We found lambda. Done. We got lambda. So let's go and find F. F requires, look, F requires the sliding velocity. The sliding velocity is equal to VW, which we just calculated, divided by cosine lambda, which we just calculated as well. So it wasn't difficult. It is 637. Now let's go to this figure, okay? And if you look over here, 600 is, this is 600. So I'm not going to be too picky. So 637 is a little bit to the right. And there you go. You got it. How much is this? Almost 0.03, which is what the book has booked. Has picked, I mean. Good. So let's move on. We got now W. Okay. Now, if we got W, then we can use it using the equations 1343 to find WZ and WY. Is that good?
Yes.
So if we do that, then also we have the equation which says that the forces on the gear are opposite to the forces in the worm, which are these. That's it. Now, once you find these forces, you will go and draw the free body diagram. So this is the free body diagram. Same business as usual. Now, if you look, worm gear is no different than the helical gear in the sense that the point over here of the engagement where the two gear engaged and the whole forces act is just on top of the axis where the bearings are. And whenever we have this, so what I'm trying to tell you over here is that this plane, this vertical plane over here has all the forces except a few. And if you look, this force is out, this out, and this out. But the remaining are acting in the plane, the red one. So once you have this, which means that this point is not shifted, it is convenient, not difficult, to do the summation of the forces, summation of the moment, and so on. This is what has been done. It was determined using a scalar formulation, simple scalar form. So this is fbx, this is fby, and this is fbz. Then in the last slide, we have fay, faz, and that's it. Fa doesn't have a thrust, while FB has a thrust because it's assumed that B, the bearing B, will carry the thrust load. We know that only one bearing will carry the thrust load, not both of them. And that's it. This is the torque. So this is almost identical to what we did before. And if you want my advice again, I would even advise you to go and not only repeat this on your own, but also attempt to solve it using the vector notation. Just keep practicing again and again and again and again. Okay. All right. Now, I'm gonna go backward, ya shabab, because I promised you I will come back to the question for the sun gear, remember? And I need to keep my promise. So let's spend maybe 10 minutes or so talking about the sun gear problem. So just to remind you, what was this problem? In this problem, we had a sun gear over here with 20 teeth rotating in a clockwise fashion, okay, connected to an arm, which is number 3. The arm doesn't have any teeth, which is connected to a planet gear. The planet gear, you can easily argue that when the sun rotates this way, the planet gear will rotate in the other way, right? And finally, we have the ring gear. The ring gear is fixed to the frame. So it doesn't rotate, and it has this 80 teeth, while the planet has 30. Okay? Now, if we want to find, as per the problem, it was asking about finding what is the RPM for the arm, because the arm is sitting on gear number, the sun gear number 2, connected to the planet gear, and the planet gear is going to rotate. So even the arm will rotate. Okay? Now, what happens is this. We derived, okay, previously, let me show you this equation, which says that the E, which is the terrain value, is equal to NL, the last gear. In our case, it is gear number 5, minus NA, the RPM for the arm, divided by NF, the first gear, which is the what, ya shabab? The sun, and minus NA, which is again the RPM for the arm. So if I go and try to solve this, I would say that E, which is equal to, let me write it in a darker tone so it become easy for you, maybe black. So E is equal to N5 minus N arm divided by N2 minus N arm. Good. Now, E as a value can be determined from this relation, the gear terrain. And if we decide to put a clockwise as negative, so clockwise as negative, and counterclockwise as positive, then E is equal to the gear ratio 2, the number of teeth 2 divided by 4. There is no 3. 3 doesn't have teeth. And then 4 divided by 5. And there you go. You have the negative sign, which reasonably gonna give you this much, minus 0.25. Now, the minus 0.25 indicate that this is the input is going to be one clockwise, for example, then the output is going to be counterclockwise. Now, in here, ya shabab, what is happening is this. You will go and put the minus 0.25, right? And then you will have N5 equals to 0 because it is fixed. NA for the arm divided by minus 100 because it is negative, and then minus NA. And if you solve this problem, you will end up with NA, which is the RPM for the arm, which is clockwise. Okay? It's negative. It means it is clockwise. I think this was all good. Now, what is the next step is to find the next requirement. The next requirement says we want to find the RPM for gear number 4. And what did we do? Using the same argument we did to establish this relation, okay, we said the relative RPM between 4 and 3 is equal to N4 minus N3. Similarly, N2 with relative N2, 3 has N2 minus N3. This is the same derivation. Look, if you go back, this is what we use to make the logic between here 2 and 5. You understand? So if we do that and then we take the ratio, we end up here. Now let me zoom this up. Now we end up in here. Now here, what do we have? We have N4, 3, the relative RPM between 4 and 3 is equals to N4 minus N3 divided by N2, 3, which is N2 minus N3. The question is, how did we obtain this ratio? Because in the solution, we obtained this ratio, and then through that, which turns out to be minus 2 over 3, we substitute these. Now look, N4 is the unknown. N3, we found it to be minus 20, correct? And N2 is minus 100. We said that from before. And this one is minus 20. So what does this mean? It means that we have only one unknown, which is N4. If I was able to determine this ratio. Now, the ratio as written here is equal to minus, which is 20, divided by 30, which is minus 2 over 3. So how did we do that? Well, if I open a note over here, I want to remind you, in the beginning of the section for train, we said that N3 is equal to N2, the number of teeth, divided by N3, multiplied by N2, which is the same as D2 divided by D3 N2. So I can say that N3 divided by N2 is the same as N2 divided by N3, which is equal to D2 divided by D3. Now, just for the record, E, the train value is equal to N for the last divided by N for the first. Correct? So if I have the equation n4 3 divided by n2 3, which is equal to n4 minus n3 divided by n2 minus n3. Forget about the 3. 3 doesn't have any number of teeth, right? There's no teeth on it. Just focus on number 4 and 2. Focus on number 4 and 2. If you look, this is number 2 and this is number 4. So if you ignore 3, in reality, it's look like this is the first and this is the last. So what does this mean? It means that the last is 4, it's like n4, and the first is like n2. Is that correct? The E.
Doctor, is the
Now,
formula not NL minus NA over NF minus NA? For,
what is it?
For E, NL minus NA over NF minus NA, NA being the arm. Or
No. You go, there is an equation which state that E equals to, yeah. Okay, so what happened? Look, what is happening right there is that we have N4 divided by N2 is equals to E. Now, we know that if we consider the difference in the rotation and we put the minus sign, then now look here, if you have 3 on the top, you will have 3 on the bottom, which means that this is the same as what? N capital 2 divided by N capital 4. That's what this is. This is what it is. And if I write to consider this is like a magnitude without taking into consideration that when the gear engaged, one of them will be opposite to the other. So formally, if I can write this E as minus N2 divided by N4, which is this one. This one now is this, which is the same as this. So this is equals to N4 minus N3 divided by N2 minus N3. Now, if you go to the solution, you will see that so what did we say? We said that this is the same as N2 and N4. So if you go and look at N2, it was 20, and N4 was 30. And the minus signs to consider the inverse of the rotation. So we'll end up with minus 2/3. Okay, and that's how we equated this with this. And we have one unknown, and that's how we got it. Okay, Shabab.
But Doctor, in this equation, they considered N5 as the last instead of N2. Or sorry, yeah, instead of N4. In this equation, they chose minus 100, right? Which is the 100. It's 100 revolutions per minute.
Yes.
Is it? Which one does this apply to? Does this apply to the sun? To which one of the gears? I'm a bit confused over there.
And the minus 100 is for the sun gear. It is N2.
But in this equation, the one we're solving, what did we consider as the last one, the last gear? Because we changed the convention, right? We chose N2 as the first and N4 as the last.
Because here we made the same analogy in the sense that the ratio is between, the relative rotation between 2 and 3 is equals to N2 minus N. Here we said N2 minus N3, and then 5 and 3. When we took the the ratio over here, we ended up with 5 and 2. 5 here is the last, right? And 2 is the first.
Yeah.
You understand that?
Yeah.
So you are just doing the same. You go and try to put them side by side and you will see it.
Okay. I get it.
Okay, this ends chapter 13. Now, let me just open up chapter number 14. So I'm just changing, ya shabab, a little bit in the design. I'm trying to make the slide more bright, and I will keep probably changing a little bit in the sizing so it become easier for me to write comments and so on. But what are we going to do in this chapter? We are going to talk about spur gear and helical gear. So number one, we have been talking about them for too long right now. But if you recall, I promised that we are going to come back to them. Actually, we didn't. We just left them, and we're going to move to them. And this time, we're going to talk about the real thing, which is this gear gonna live the number of cycle I want it? Is it going to be good for the applications? I know it has to have this number of teeth. I know it should have this diametral pitch and so on, but it is not a rigid body. It is a deformable body. And when it is under the action of load, how is it gonna perform? Is it gonna survive or not? So this is the reason why we have this chapter. Now, what I want to tell you is this very important, which is a really, really important idea for you. I am very happy that the department decided that we are going to talk about spur gear and helical gear, and luckily, both of them are in the same chapter. There is another chapter, which is 15, and it is about bevel gear and worm gear. Exactly the same way. But we are not going to cover it. And this is very interesting. Why? Because, ya shabab, we would never be able to teach you everything in here. And even when you go to company, you would keep learning until maybe one day you understand everything in that company. And if you go to another one, you will have to go through the learning curve again. So this concept of self-development is very important, which means we are going to talk about the spur gear and helical gear here, strength and life and stress and so on. But we will assume that if you understand that, you will be able to go and find the same analysis and understand it for any other type of gear, any other. The same concept and logic applies. There will be some sort of a stress equation, there will be some sort of a allowable something, and then you compare. So this is very important because it is better to cover other topics like belts and clutches and brakes and so on, and this is good enough for you. So this is very important. Okay, now the outline of the chapter is in front of you. There are two omitted sections, and honestly speaking, the first one has the word Lewis. Lewis is a person who is the first to establish an equation that helps calculating the stresses, especially, particularly bending stress in gears. And Lewis equation becomes so fundamental. So you will hear about it a lot, but we're not going to go over the section to cover Lewis. We're just going to mention it. But what are we going to do is this. We're going to talk about two stress equations, which are the AGMA stress equation. And what is AGMA? I'm going to tell you in a minute. But what is important, without going through this boring outline, like talking about number 1 and 2 and 3 and 4 and 5, which you can do by yourself, is this. Look at it. Just, I want you to go with me now and look at it. A geometry factor, elastic coefficient, dynamic factor, overload factor, surface condition factor, size factor, distribution factor, hardness factor, cycle factor, reliability factor. What does it remind you of? Anyone?
This is stress chapter on stresses on shafts and stuff from 307.
It's actually the marine equation.
Yeah.
You know, the marine factors, which is a very important analogy. There are 2 equations which we are going to talk about, which are basically a multiplication of some factors. And these factors will handle the most significant part. Too many things happen to the gear: the rotation, the contact, the friction, the loading, the size, the temperature, too many things. So here we have a very clear way to understand each one of these factors, put them together, and then make a decision. Let me show you this image, ya shabab. This image has a lot of memory because I think when I studied in KFUBM back in, I took 308, right after I finished my co-op. I was an applied student, and I remember the textbook, if I am not mistaken. This was the textbook. I had this picture on the cover page. Okay, this was back in 2001, 2002. Actually, 2002 and 2003. So what is this picture? Let me, as a motivation, let me talk about it for about 5 minutes, and then we will move on. This is a picture of a photoelastic analysis. What is photoelasticity? Photoelasticity is a physical phenomenon. You have a transparent material here. It looks like this is a transparent gear, right? It's not made from metals, which is true. This is one of the well-known photoelastic material is polycarbonate, which is available in the market. So if you take a piece of polycarbonate and then you machine it like this, full profile, conjugate action, and convolute profile, 2 gears, you mount the gear on shaft and then you rotate them. Of course, it's made from plastic, so you cannot imagine that this is going to take 1 horsepower or something. No, a little power. So what happens is that if you put this between a source, a light source, and a filter, the light source has to be white, and then the light passes through the polycarbonate with the teeth and so on. And then there is a filter in front of you, which is a monochromatic filter. Mono means 1. So it filters out all other light spectrums, you know, the red, the green, the yellow, and let a monochromatic light passes through the polycarbonate. The result that you are going to see out of that is this. What are these? These nice round butterfly looking colors. These are called the fringes, and they are directly related to the state of stress of the material. So if you look carefully over here, you will see that, let's look at the tooth on the top. The tooth in the top has apparently 3 significant regions. 3. The first one is this, the second one is this, and the third one is this. The rest is, you know, very clear that this is a direct influence of that field to other. So, but these three are the most significant one. Well, let me tell you, in the 1950s, people didn't have digital computers and so on. So photoelasticity was a star. It was a star. This is just even before the invention of the electronics, the strain gauges and other. And by the way, even if the strain gauges were there at the time, strain gauge is an electronic piece that you put it and you wire it and it gives you strain. You don't see things, you just see numbers. But this one is visual. You can see the location where the stresses are crumbling, coming together. Well, to make it short, these two stresses are due to bending. And particularly, since this is pushing, this one is pushing this to the side, the reaction is this, so we can expect that this is tension and this is compression. And we know that once we talk about bending, we're good. We're gonna look at both sides. The equation works for both sides. So these two lumps of colors has been identified. What is the third one? The third one is coming from contact. And I told you this when we talked about bearing. I told you that the bearing, when the ball bearing sit here, it creates a field of stress when it is being pushed against the surface. There it is. Let me clean it up so you can see it. Now, contact, ya shabab, is a mechanics by itself, an entire field called contact mechanics. It's part of solid mechanics. Solid mechanics is the mechanics that deals with solid bodies, something hard being pushed against another or being subjected to some sort of loading. So what would you expect? We'll have the two equations, one of them to it is so interesting. People in the 50s, they saw this and they saw, so let's build two equations, one for the bending and one for the contact. Straightforward, right? Straightforward. No playing around. Don't give me something I don't see. There it is. Bending and contact. Is that clear? So now, the two fundamental equations then are the bending stress equation and the pitting resistance. The pitting is this come and touch, go, touch, go, touch, go, touch, go. They call it pitting. And it is being, derived based on the basics of contact stress, which is coming from the contact mechanics. Okay. Now, who is AGMA? AGMA is the American Gear Manufacturer Association, a very well-reputed organization where they put too much effort to standardize the design for gears. It is unbelievable, ya shabab, how gears are important. You can imagine that within 10 years maybe or 20 years, we may not see an internal combustion engine car, but there is gonna be a gearbox in the electrical car. There's no doubt about it. You need to control speed, right? So gears are so fundamental. This is very important. Now, what is the first equation? I'm gonna go over the equation, try to make you look, comfortable. And then next class, we're gonna handle them. So get ready for what you expect. KA, KB, KC, KD, KE, KF, you remember? Same thing. So this is the stress equation. And it has been given to us here in US customary unit and SI unit. And be careful. There are, for example, F over here is the face width in US, while B here is the width in millimeter in SI unit. So be careful. So let's start one by one. The first one is WT. The WT is the transmitted load, and it is either in pound force or in a Newton. Good. Then the next one is KO. KO is the overload factor. Is a factor that was designed to probably elevate the stress, state of stress, based on the fact that there are instances of overloading while the gear is in operation. Then we have KV. KV is the dynamic factor, which is very reasonable. In the end of the day, gears are always in motion. They never stop. So the dynamic action there is very important. Then we will have KS, which is the size factor. Okay. And then we have over here, we have the transverse diametral pitch, or in millimeter, we have MT, which is the transfer metric module, right? You know that they are kind of the inverse. So this is why one of them is up, one of them is down. So then we have a Km over here equivalent to Kh. So Km and Kh are the load distribution factor. One of them is for the metric, one of them is for the US. Then we have Kb, which is the trim factor. The trim thickness is how much material below the teeth, and we're going to talk about it. Then what do we have? We have a J here and Yj, which are the geometry factor for bending strength. Okay. Now, let me show you. Of course, here it says that this equation is supposed to take into consideration. Shabab, can you give me 1 second? I need to take a phone call. Okay, let's get started again. So what are these equations? Of course, this is a summary of what these equations takes into account: the transmitted load magnitude, overload, dynamic effect, size, geometry, distribution of the load, and the rim support, and so on. So, inshallah, ya shabab, while we are talking about each one of these letters, okay, you will have a very clear idea about what they are. Oh, it is already 12:48. So I'm going to stop here, ya shabab. I don't want to take too long from your time. I think this is enough. We'll see you, inshallah, next week, and then we'll continue. Let me just take the attendance, and then you'll be ready to go.